All right, guys, today we're going to learn about the ideal gas law. We've learned last week about the three basics. If you remember those, we've got Boyle's law, we've got Charles' law. All right, so we've got Boyle's, which is dealing with pressure and volume. We've got Charles' law, which is dealing with volume and temperature. We have Gay-Lussac's law, which is dealing with pressure and temperature. And then we talked about Dalton's law of partial pressure. All right, where you basically take the total pressure, all right, and you add up all of the gases that you may have. All right, and continue on. It could be 15 gases. It could be just a couple gases. It could be whatever. So those are when we're dealing with certain situations, excuse me, where we're changing one variable, or we can put them together, these three together, in what's called the combined gas law, where you've got P1 V1 over T1 equals P2 V2 over T2. And that is what is in your reference packet. And if you actually look at your reference packet, all right, if we look back here, all right, we can see if we go to our formula sheet, which is right here, we've got those built into the combined gas law. And notice over here, which shows us pressure, volume, temperature, so we know what the variables are. Here's Dalton's law of partial pressure. Okay. All right, so then we are given the combined, and you can just cover up whatever piece you don't need. Whether if you have just volume and temperature, you can cancel out the P's, or if you have just pressure and temperature, you can cancel out the V's. And same thing with temperature, you can just cover those up, like I showed you last week, so it's not a big deal. Fortunately for us, we also have the ideal gas law. So most of these formulas that we're given in this unit, we have right there in our formula sheet in our reference package. You don't have to remember stuff. All right, it's there for you. Don't be lazy. Go and actually use it. All right, so you need to get your reference packets out if you don't already have those. Yeah, that means you in the back, get them out. All right, quit talking at the same time. All right, so here we go. I'm going to go ahead and erase this. So now we're going to start talking about the ideal gas law. Now, is there such thing as an ideal gas? No, we know that from our last unit. There's no such thing. That is this gas that we have that would be perfect for us, but under real life conditions, we do have forces of attraction. There's no such thing as an elastic force or elastic collision, excuse me. All right, so we use this ideal gas law when we're trying to. So this ideal gas law, what it allows us to do is that we can now take a certain amount of sample, let's say for this first example 12 grams, we can go from grams and we can figure out anything involved, any pressure, volume, moles, or temperature based on the amount that we have with those certain conditions. So again, why this is important is as scientists, these are the things that we're doing all the time, trying to produce a certain amount of something in a lab setting where you don't have ideal conditions, but you roll with whatever you have. You're not going to be at perfect pressure, or maybe you need to crank up the pressure. So, all right, to get the reaction to go. What this ideal gas law allows us to do is it relates all these variables that we've talked about. We've got pressure, we've got volume, we've got temperature. Remember, the key here is temperature has to be in Kelvin. Why is that? It's because Kelvin has no negative numbers. We can't have a negative pressure or a negative volume, so we have to use a temperature that is always positive, which again is Kelvin, because remember, absolute zero is the coldest it can get, therefore it can't go negative. Celsius, we can have negative degrees Celsius, but again, that would give us a negative pressure or a negative volume. So you've got to make sure if you're not given your temperature in Kelvin from the start, you need to convert that right away. But again, this is just like any of the other formulas. We're going to be given 4 of the 5 variables, and we have to then solve for the unknown. It's plug and chug, folks. It is that simple. This is not like, stoichiometry problems we've done where we've got to go through a whole step of pieces. You're given pretty much everything you need. Therefore, that's all you got to roll with. So you got to be able to solve for that unknown variable. And again, like I showed you on Wednesday and Thursday, I highly recommend solving and rearranging your variables in your equation first before you start to actually plug anything in, because then it's so easy to lose numbers. All right, so just go ahead, solve that first. Make sure you write down all of your variables, because that's going to tell you what you need. It's going to be your guide. Remember to, like I always say, let your units drive your math. Okay, so here we go. Let's take a look here at this problem. All right, pressure in atmospheres. Why is it in atmospheres? It's because of our gas constant. Remember, if you take a look at your reference packet, all right, give me a second. I'll pull it up here. All right, if we take a look here at a reference packet on the front page, so like I said, get them out. You're going to need them. Okay, when we take a look right here, we've got our gas constant. There are 3 different ones. You can use whichever one you want, but I would highly recommend using the same one every time to just be consistent. All right, every problem you see, I'm going to be working this out, so that means I'm going to need moles, I'm going to need Kelvin, I'm going to need atmospheres. The only difference between them are their pressure units. Okay, so the more you switch up which R you're going to use, the greater the chance of making an error, unless you are diligent and write things down, which I know a lot of us were not diligent. Okay, so keep that in mind as we go throughout. You're going to see me work every single problem out using the atmospheres one. All right, so here we go. It says, what is the pressure? So what am I looking for? Pressure equals question mark. Exerted by a 12-gram sample. So that's mass. So I've got 12 grams of nitrogen gas. Remember, it's N2. Why is it N2? Diatomic, it's part of Brinkelhoff. Volume equals 10.0 liters. Temperature equals 25 degrees Celsius. I want to convert that right away. Add 273. Therefore, it's going to be 298 Kelvin. R is my constant. It's going to be 0.0821. You'll hear me call them Latham over Molch. All right, it's just an easy way. It's really liters times atmospheres divided by moles times Kelvin, but I'm just going to call them that because they're multiplied together. It's just easier to say. So I'm looking for pressure. All right, so I'm going to solve my equation for pressure. I'm going to do it up here where I have some more space. PV equals nRT. All right, PV equals nRT. There's a song. If you check out my YouTube channel, when you go back and rewatch this video if you need to, the song will be on there for you. I know you guys like them. You can laugh all you want, but you can't deny it that you remember stuff that way. Here we go. Get P by itself dividing by V. Those will cancel out. So my new formula, P equals nRT over V. Do I have P? No, that's what I'm looking for. I've got R, I've got T, I've got V, and I've got to get N. Do I have some piece of information that will allow me to get N? Absolutely. That's going to be my mass piece. So I'm going to write this down. I've got P equals nRT over V. I'm going to erase this space up here to use this for my work. All right, so I've got 12 grams. 12.0 grams of nitrogen. Here we go. This is some stoichiometry. But guys, this is simple. You're going from grams to moles. If you are struggling with this, you need to come to tutoring. All right? You've got to practice it. That's the only way. So set up my T-chart. 1 is always down there. Grams of N2. Let my units drive my math on the bottom. That means I'll have moles of nitrogen on the top. Which one? When you have grams and moles in the same fraction, which one gets the... which one is going to get the number 1? It's always moles. 1 mole of nitrogen. Now, this is where remembering Brinkelhoff is key. It's that N2, so that's going to affect our mass. So when we plug that in, 14 is, so we got 14.01 is the mass of nitrogen. We got to multiply by 2. So our molar mass here is going to be 28.02. Cancel those out, cancel it out. So how many moles? N is going to equal, when we do the math, go ahead, get calculators, go ahead and solve it. You should end up with 0.43 moles. Okay, now we've got everything. We've got N, check. We've got R, check. We've got T, check. And we've got volume, check. So now all we have to do is just plug and chug. P equals N, 0.43 moles. Keep your units with it. Times R, 0.0821 Latham over Molch. Moles are going to cancel out because it's on the bottom of this fraction. It's on the top here. All right, times it by temperature, 298 Kelvin. That's going to cancel out as well, top and bottom. Then it's all divided by your liters, which is 10. All right, it's on the bottom here. It's on the top there. It's canceled out. We're left with atmospheres, which is a good pressure unit. So go ahead and solve for this. You should end up with a pressure of 1.05 atmospheres. 1.05 atmospheres. Pretty easy. My hope is that it is compared to any stoichiometry we've done. It's just a formula, guys. You're given 4 of the variables. The only big thing you're going to have to do is you may have to take the mass to moles. But we know how to do that. We've done that since Unit 6. All right, find the molar mass using your periodic table, which again is why you need to have your reference packets out. You've got to use them. Don't be too lazy to use the resources that you have. All right. You guys are going to practice. I'm not sure if these are the right pages, but it says ideal gas law worksheet. All right, you're going to do numbers 1 through 4. I'm going to work those out here. Sub, you can pause the video, all right, and then give them about 10 to 12 minutes, and then play it, and I'm going to work out the solutions to those. All right, so if you go over here, ideal gas law worksheet, I'm going to do numbers 1, 2, 3, and 4. All right, so take a few minutes to do that. All right, so you should have worked those problems out. I'm going to go work them out so you can see how I did them. You can check your answers to these problems. So here we go. How many moles? So N is what I'm looking for. I'll occupy a volume. My volume is 2.5 liters. Pressure equals 1.2 atm. My temperature equals 25 degrees Celsius. Got to convert that to Kelvin right away, plus 273. There's going to be 298 Kelvin. Then my R is the only thing I'm missing. Again, that's a constant, so I get that from my reference packet. 0.0821 latom over molk. All right, so PV equals nRT. I'm solving for N. Get that by itself. Divide by RT. Divide by RT. So N equals PV over RT. Now I can solve, start plugging things in. 0.2 atm times my volume, which is 2.5 liters, all over 0.0821 latom over molk, times your temperature of 298 Kelvin. So you're going to be left with moles is all that you'll be left with. So you have a final answer that is 0.123 moles is what you should have. Moles of oxygen. Right? There's that. All right, number 2, it says what volume, so we're looking for volume, 2 moles make, so N equals 2.0 moles, all right, of nitrogen, N2. All right, our pressure equals 720 torr. Now I can change up my R, or I can convert this to atmospheres. I'm going to convert it to atmospheres. You can make the choice. I like to be consistent, use the same R value every single time. 0.95 atm. And my temperature equals 20.0 degrees Celsius. Add your 273, so that's going to be 293 Kelvin. And again, my R, since I kept my pressure in atmospheres, it's 0.0821 latom over molk. So PV equals nRT, divide by P, those cancel out, divide by P. V equals nRT, so N is going to be 2.0 moles times R, 0.0821. Temperature, 293 Kelvin. All over my pressure, which is 0.95 atm. Go through and do the calculation very quickly. 2 times 0.0821 times 293 divided by 0.95. We get a final answer of 50.6 liters is what we should have there. Number 3, what pressure? So we're looking for P. We have mass now. All right, we have a mass of 25 grams of CO2. So we got to convert that to moles. All right, mass isn't going to do us any good. All right, so we're going to divide that by the molar mass, which is going to be 44 grams per 1 mole. 25 divided by 44, we get 0.56 moles of carbon dioxide. So now we have our N. There's our N value. Temperature T equals 25 degrees Celsius plus 273. All right, that's going to equal 298 Kelvin. Volume equals 500.0, or just point, mils. What do we have to do here? That's milliliters. We need liters. So that's going to divide by 1,000. We get 0.500 liters. Again, our since we have moles, we have Kelvin, we have liters. R is going to be 0.0821 latom over molk. So PV equals nRT. Divide by V from both sides. P equals N. My N we said was 0.56. And for showing me all your work, you can get partial credit. If you miscalculated that but did everything else correct, you're going to get partial credit. The more work you show me, the more credit I can give you, potentially. 0.0821 latom over molk. And then your temperature is going to be 298 Kelvin. All over our volume of 0.500 liters for sig figs. So my new pressure that I'm going to have, do the math out, 0.0821 times 298 divided by 0.5, we should get a pressure of 27.4 atmospheres. And the last one, we're looking for temperature. We have grams, so 5.0 grams of Cl2. Notice it's a Brinkelhoff, so it's going to change the mass, 70.9 grams. All right, our N value, when we do that math out, is 0.071 moles. There's our N value. All right, pressure equals 900 torr. I'm going to convert that to atmospheres. 900 divided by 760. 1.18 atm. Volume. Every single one of these you got to kind of convert right here. Volume equals 750 mils, which is going to be 0.750 liters. R value is going to be the same as what we've had. And that's the one piece that's the same every time, unless you decide to change it up. Me, I'm not deciding to change it up at all. So PV equals nRT. We're going to divide by N and R. So we get T equals P, which you said was 1.18 atm, times your volume, 0.750 liters. All over your N and R, we said N was 0.071 moles, multiplied by 0.0821 latom over molk. All right, everything will cancel out except for Kelvin, which is a good temperature unit for us. 1.18 times 0.75 divided by 0.071 divided by 0.0821. We get a temperature of 152 Kelvin. If you have questions about these, save them for when I get back. We'll talk about them on Wednesday. Your assignment now is to do all of the ideal gas law problems that are in your note packet, which should be on page number 7. You're doing the bottom 10, numbers 1 through 10. On a separate sheet of paper, you got the formula right there, gives you the constant. I want to see all your work for full credit. All right?